I'm so glad you were able to make it to section 5 of this course. In this section, we will learn how to leverage Wireshark 3 to perform deep packet inspection of common protocols such as TCP, UDP, IP version 4 and 6, and ICMP version 4 and 6. In this video, we will learn how to use Wireshark 3 to perform deep packet inspection for TCP header. As you know by now, TCP is a transport layer protocol. It provides process-to-process communication, meaning that the transfer of data takes place between individual processes executing on end systems. It is stream-oriented as well. We mean that the data is sent and received as stream of bytes. Unlike UDP, that we will see in the upcoming video, or IP, that divides the bits into datagrams or packets. However, the network layer that provides services to the TCP sends packets of information, not stream of bytes. It's full duplex, meaning that the communication can take place in both directions at the same time. Connection-oriented, unlike UDP, TCP provides connection-oriented services by defining three phases, which are connection establishment using three-way handshake, then data transfer, and then connection termination. It is a reliable protocol that uses checksum for error detection and attempts to recover lost or corrupted packets by simply doing a retransmission. And of course, it's slower than UDP. So TCP continuously receives data from the application layer. It divides this data into chunks where each chunk is a collection of bytes. It then creates TCP segments by adding a TCP header to the data chunk. So a TCP segment is just data with a TCP header. And then TCP segments are encapsulated in the IP datagram. It is worth noting here that a TCP connection is uniquely identified by using not just the port, but a combination of port number and IP addresses of sender and receiver. The IP address indicates which systems are communicating. Meanwhile, the port number indicates which end-to-end sockets on these systems are communicating. So let's deep dive into the TCP header. Usually, the TCP header can range from 20 to 60 bytes. Each TCP header has 10 required fields totaling to 20 bytes. So the minimum size of a TCP header is 20 bytes or 160 bits in size. It has an additional information field that can have up to 40 bytes. So the minimum TCP header size is 20 bytes and the maximum is 60 bytes. So let's see here what are the fields of that header. We have source port, destination port, sequence number, acknowledge number, header length, reserved bits, flags, window size, checksum, urgent pointer, and options and data. If you want to see those in sizes, here you go. Before going to Wireshark to demonstrate and explain the header in details, let us first take a look at how data is transferred between a sending and receiving endpoint. So all the data bytes that are to be transmitted are numbered, and the beginning of this numbering is arbitrary. Sequence numbers are given to the segments so as to reassemble the bytes at the receiver end, even if they arrive in different order. So sequence number of a segment is the byte number of the first byte that is being sent. Acknowledgement number is required since TCP provides full duplex services. Acknowledgement number is the next byte number that the receiver expects to receive, which also provides acknowledgement for receiving the previous byte. To be more clear, in this example, we see that client that is on the left sends acknowledgement number of 2001, which means that it has received data bytes till byte 2000 and expects to receive 2000 1 next. Hence, the client on the right sends data bytes starting from 2001. Similarly, since the client on the right has received data bytes till byte number 14001 after the first data transfer from the client on the left, therefore the client on the right sends acknowledgement number 14002, the bytes that expects to receive next. Now that we explained the sequence number and acknowledgement number into details, let's go to Wireshark and do our deep packet inspection. Open Wireshark and open any recent capture that you've done. I'll just open the SMB capture we've done earlier. And once this loads, in the display filter, type TCP. And just select any frame here. I'll just select this frame. And we'll go here. As you can see, this is the encapsulation. The layers are shown here. I'll just expand TCP. So as you can see, we have a source port and a destination port. The source port is a 16-bit field. It identifies the port of the sending application. The destination port is 16-bit field as well, and it identifies the port receiving application. Stream index is a field specifically maintained by Wireshark in order to differentiate between the TCP streams. The sequence number and the acknowledgement number are 32-bit fields number. As we explained earlier, TCP assigns a unique sequence number to each byte of data contained in the TCP segment. This field contains the sequence number of the first data byte. As for the acknowledgement number, it contains the sequence number of the data bytes that the receiver expects to receive next. It is always the sequence number of the last received byte incremented by 1. Here we can see a relative sequence number. You can just press right click, open protocol preferences, and uncheck relevant sequence numbers because the number can get huge. So relative sequence number, it means the sequence number relevant to the current TCP stream. We'll put that again. Going down, we see here the header length. It says 32 bytes, and if you press on the TCP header here, below you will see 32 bytes as well. So the header length is a 4-byte field, as you can see. It contains the length of the TCP header, and it helps in knowing from where the actual data begins. So as we said before, the minimum length is 20 bytes and the maximum length is 60 bytes. So you always have to multiply the value here in the header length by 4 bytes to get the header length. In binary form, this represents 1, 2, 4, 8. So the value we have here is 8. 8 multiplied by 4 bytes, we have 32 bytes in size. If we expand the flags here, we will see the reserved bits that are not usually used. And down below, we will see the control flags, which are the urgent pointer, acknowledgement, push, reset, synchronize, and fin. Make sure not to mix the concept of the flags here, the acknowledgement and the sync, with the sequence number and the acknowledgement number. The flags here are mainly to set up the connection and terminate the connection. The fin stands for terminating the connection. The syn is just to synchronize the sequence number. Reset is just to stop the connection. I don't want to talk to you anymore. Push is to request for push. The acknowledgement is acknowledgement number, and the urgent flag is an urgent pointer. Going down below to the window size value, this field tells the window size of the sending TCP in bytes. In other words, how much data I can receive without being overwhelmed. The scaling factor here is 256, and the window size is 67, and the actual calculated window size is the multiplication of these two numbers. The checksum field holds the checksum for error control. It's error detection and not correction. It is mandatory in TCP as opposed to UDP, as we will see next. You can see that here that the value is unverified. You can right click, go to protocol preferences, and press on validate the TCP checksum if possible. The urgent pointer is used to point to data that is urgently required and needs to reach the receiving process at the earliest. And down below we have the options field, which is currently 12 bytes in size.